we have been talking about solid state transformations, and we started with precipitation. And we looked at the basics of precipitation, where is the driving force coming from, and also we started looking at where is the barrier for precipitation. We said there are two barriers, one is the surface energy and two is the strain energy, right. These are the two barriers when we are talking of solid state transformation. Any solid state transformation in principle will have both these barriers, and precipitation is just one of them. And when we are talking of liquid to solid, this part will not be there, this we have already seen it, and only the surface energy is what we talk there. Now when we are looking at both these things, the system wants to somehow minimize the overall energy that it has to spend. This is the energy that it has to spend. A summation of these two energies is the energy that it needs to spend for creating a precipitate. If that is the case, the system would like to choose that particular precipitate which has a minimum combination of strain and surface energy. This is what actually we were looking at in the last class, and that is what leads you to the formation of what are called transient phases. For example, in a number of systems, the final product may have a structure which is entirely different from that of the parent phase. Particularly, let us say an example of aluminum copper itself, the theta phase, which is an orthorhombic, is entirely different from in its structure. There is no real similarity in terms of any of the atomic planes. If you look at any of the atomic planes in orthorhombic structure, there is no real compatibility with any of the planes in the FCC type of structure, which is aluminum is FCC. So the matrix is FCC. So in such a case, when you have such a phase trying to precipitate out inside the grain, all the problem comes only because the precipitation has to occur inside the grain. Why it has to occur inside the grain? Because the temperature is low. Our precipitation is happening at a temperature which is very low for the diffusion to happen, so that the atoms move from the center of the grain to the grain boundary and nucleation to occur there. As long as nucleation is occurring at the grain boundary, there is absolutely no problem. Any kind of precipitate, whether it is compatible with the matrix or not compatible with the matrix, can precipitate at the grain boundaries, because grain boundaries are the regions where you can accommodate. Strains can be accommodated, and already grain boundary has a higher surface energy. So with respect to that, this surface energy can be accommodated. So because we are now talking about nucleation within the grain, somewhere inside the grain, that is where we have to worry about this. This is what we started looking at in the last class, and we said basically it looks first of all what is the misfit between the two, and also the system also looks for what is the is there any possibility of a phase which can have very low interfacial energy with the matrix, and such phases are what we call them as coherent interfaces. A coherent interface is that where there is a continuity of lattice planes across the interface. For example, if you think of a matrix and inside that you have a precipitate, and precipitate, let us assume that the precipitate has the same structure as that of the matrix, and it has certain atomic planes. If I draw certain atomic planes here, and then also the matrix also has certain atomic planes, and these are all one single grain. Let us assume that inside one single grain a precipitate has formed, and this precipitate is trying to have a compatibility with the matrix. And when is this compatibility possible? When the atomic planes that are there in the matrix have similar interplanar distance with respect to the precipitate, then what you see is there is a continuity of the atomic planes. whenever there is a continuity of the atomic plane, any plane, it can be a 1 1 1 1 plane, 1 1 0 plane, some plane, if it can have a continuity from the precipitate to the matrix, then we call it as a coherent interface. And for this to exactly have matching, what you need to see that the misfit should be actually 0%. That means what? The lattice parameter of the precipitate should be equal to the lattice parameter of the matrix, because interplanar distances are related to A. All of you know in cubic what is the relation between D and A in cubic? Prerna, do you remember? What is the relation between D and A? D, which is the interplanar distance, A, which is a lattice parameter in cubic. A by 2. Correct. So we know that D is A by under root h square plus k square plus L square. This is only for cubic. So if that is the case, I know that if A of matrix and precipitate are the same, then the D for any plane, whether it is 1 1 0 or 1 0 0 or 1 1 1, for them you would also see the D also will be the same. And if the D is same, the interplanar distance being the same, then you would see there is a perfect matching. And this is a very ideal situation, very difficult to really see, and there are very few cases where such a thing happens. One such case is gamma gamma prime, where gamma is a matrix which is a nickel base superalloy, and gamma prime, what is gamma prime? Ni3Al. And there are also another situation, something like Al3Li, which is called delta prime, and in an aluminum matrix. There are a few such examples. Al to Ag is another example, aluminum silver phase diagram. So whenever you have such a situation, you will see that there is a matching. In case the lattice parameter of the matrix is different from that of the precipitate, what should happen? You will see some kind of for example, let us assume that the precipitate is like this. This is the d spacings for a particular plane. For the same plane here, you would see that what I would like to say is that this spacing is slightly larger than this spacing by about a few percent, let us say. If the d spacing is slightly larger, what happens is there will be some kind of a bending at the interface of the planes. In order to maintain the continuity, the atomic planes will have a kind of a strain that comes in, because there is a bending of the atomic plane at the interface, and that causes what is called coherency strains. In order to maintain the coherency, the system tends to have some kind of a strain, and this strain can be accommodated up to a certain value. We talked about some time back, whenever you put a solute into a solvent, also a strain can be accommodated up to certain extent. Beyond that, the solute is rejected. Similarly, up to certain extent it maintains, and if let us say the distance between the d spacings here and the atomic planes here and the distance between the atomic planes becomes much larger difference, then what happens? Then you would see, for example, let us say this is the situation, that the d spacing here is much larger than the d spacing there. Then what happens is, in a unit distance, the number of atomic planes, any particular plane that we are talking about, is different for the matrix and the precipitate. So that means across the interface, if I look at it here, below the interface you have certain number of planes in a unit distance of x, and above that you have a less number of planes. So, as a result you do not have a one-to-one matching for every plane which is there in the precipitate, you do not have a matching plane in the matrix. Then what happens? What happens is some of the planes you will have a continuity and some of the planes are left out, and this is exactly similar to something like a dislocation. What is a dislocation? You say you have an extra plane of atoms below, you have a extra plane of atoms above a particular plane. So, exactly you see, that means you are creating dislocations. These are called interfacial dislocations, and these are also called misfit dislocations, because the dislocations are coming because of the misfit, and that is why they are called misfit dislocations. And these, the moment you generate misfit dislocations, we cannot call this anymore as a coherent interface, we call now this as a semi coherent interface. They are called semi coherent interfaces, partially coherent, and if this keeps on increasing, then what you see is that the number of dislocations will keep on increasing. If the misfit keeps on increasing, that means for any given number of atomic planes in the precipitate, the number of atomic planes on the matrix, it continuously keeps on decreasing, let us say, because the spacing is increasing. One of them is increasing with respect to the other, we are only looking at the relative change. So, if that is the case, you will see that as this increases more and more with respect to this, you will see more and more planes within the precipitate are left out on the other side, you do not have a matching planes. So, that means you have more and more dislocations generated, and every dislocation is associated with certain energy. That means the energy of the interface is increasing, every dislocation has an energy, and that is the reason why we actually consider dislocations also as one of the heterogeneous nucleating sites. Why? Because if you can have a dislocation, nucleation there, the energy can be reduced, because dislocation has an energy. Where is this energy coming from for the dislocation? Because there is a distortion above and below the plane. If you remember if you have atoms like this, let us say, you see that there is a strain associated there, and this strain is what causes the energy of the dislocation, and so that is what is going to increase as more and more dislocations come, and at some stage the overall energy is so high that the system prefers not to have any coherency, and that is what we call it as incoherent precipitates. Usually you get incoherent precipitates when the structure of the precipitate is entirely different from that of the matrix. As long as the structure is the same, the system, the only difference now is only lattice parameter, the system tries to have either coherent or semi coherent, unless you the misfit, you get incoherent when the misfit, which we call it as delta crosses about 15 to 20%. Assuming that the structure is the same. The moment structure is different, then it is not possible to have any coherency. So, it automatically irrespective of what is the lattice parameter of the precipitate and the matrix, you get a incoherent precipitate automatically. The moment structure is same, then we look at this, and usually if the delta is less than about 5%, you get completely coherent interfaces, and gamma prime, such cases are all something like that, where you have the delta very small, and such a case you get this. So, this is in general, this has nothing to do with thermodynamics, but coming because of the strain, and because strain energy is also part of one of the thermodynamic parameter, we need to discuss this. So, this is also going to decide what is the type of precipitate that is going to come out. Now, what we are talking is, we are assuming that the coherent precipitate is coming out, and what is the shape of this coherent precipitate? This is what we were talking in the last class. what should be the shape of the coherent precipitate, assuming that it is coherent. If we think that it is coherent, that means strain is not too large. If the strain is not too large, then the strain energy is too small. That means delta G epsilon is small. If delta is small, once that is the case, then what decides is the surface energy. Once for a given precipitate and matrix, if this is small, the system will choose that particular shape which has the lowest surface energy. And coherent interfaces, mind you, coherent interfaces always will have the lowest surface energy, because there is continuity. It is as if, like, if I give you an analogy, it is like a low angle grain boundaries with respect to high angle grain boundaries. A low angle grain boundary has a lower energy, because the extent of misorientation between the two grains is very small, and the more the misorientation, the higher the energy of the grain boundary. Exactly similarly, because there is a continuity of the planes at the interface, coherent precipitates always have the lowest energy, and incoherent will have the highest, and the semi coherent will have somewhere in the middle. So as long as you say a coherent precipitate is forming, it will always have a lower surface energy. So we are saying that strain energy is already low because the delta is small. Then what should be the shape? That is where you will see the shape automatically turns out to be a sphere, because sphere has, whenever we are talking of overall energy, you have to remember it is V into delta G epsilon plus A into gamma. That is what has to be minimized. This is the overall thing that has to be minimized. The system wants to minimize this, and once this is small, and if this is also small, it would try to have a smaller area, and that is what is a sphere. Sphere has the smallest surface area. So once it chooses a spherical particle, you can see this overall can be minimized, and that is how you see spherical precipitates come only when the delta is very small. When the delta is large, and even you will see that in some of the cases where the spherical precipitates come, when they grow to bigger sizes, you will not see these spherical precipitates maintaining their spherical nature. In a liquid to solid, there is a possibility that if you have a spherical precipitate, spherical particles forming from the liquid to solid, they can still grow as spheres. There is no strain associated there, because liquid everything can be accommodated, all the strain can be accommodated inside the liquid, whereas if you have a spherical precipitate which is growing inside a solid, then in order to maintain the coherency becomes very difficult for a spherical. If you think of a curved interface, if you have atomic planes, curved interface, to maintain the coherency on a curved surface is not easy. Maintaining a coherency on a flat surface is easy. As a result, what happens is, as it grows to bigger and bigger, this coherency becomes more difficult. So it slowly changes into shapes which are like this. That is why gamma prime you see cuboids. When they grow, they become cuboids. At the nucleation stage, they are all spheres. If you look at them at the initial stages of precipitation, they are all spheres, and then they become cuboids. This is all in the cases where the misfit is small. If the misfit is large, that is what yesterday we have seen, if the misfit is large, then the system wants to somehow see that you do not anyway the strain energy with a sphere is always higher. That is what we have seen, the highest is with the sphere. So sphere is avoided, and then the other two possibilities are, one is a plate like precipitate and another is could be a rod like precipitate, and you see that a plate like precipitate has a better compatibility, and as a result in a most of the cases you see plate like precipitates, and that is what you see in most of the cases, that plate like precipitates come because the delta is larger. So this is all more of somehow minimizing the overall but this is all at the starting only. We are talking of a starting, and where you have only come to an intermediate stage. Why intermediate stage? Because if you start with a supersaturated solid solution, for it to give you alpha supersaturated solid solution, to give you alpha plus theta, though there is a large driving force, the activation barrier is also large. So what the system does is, system chooses that particular structure which has a lower activation barrier. That means lower combination of these two. What is the activation barrier? It is this which is the activation barrier, combination of these two is the activation barrier, and that it tries to minimize that and then gives you another precipitate with a lower activation barrier, but at the same time you see the energy of this will be higher than the energy of this, because that is after all a metastable phase. So a metastable phase comes out of this, and there is definitely a driving force for this to come, because this has a lower energy than this. So from a supersaturated solid solution, another phase which has a lower energy than this comes out, and that is what in our case is what we call it as GP Jones, alpha plus GP Jones, and that goes through next stage and then the next stage, and then finally you reach this level. So it goes to theta double prime to theta prime and finally to theta. As the precipitate starts growing to bigger and bigger sizes, it slowly changes from the original state of supersaturated solid solution to the final equilibrium shape, which is the theta, in a number of steps, because at each of the steps, if GP Jones want to jump to theta, again the activation barrier will be large. So it tries to see that the same thing happens in steps. This is what people call it as Ostwald step rule. Which basically talks about whenever an activation barrier for a particular transformation is very large, the system tries to achieve that final equilibrium stage in a number of steps, where each of the step the activation barrier is much smaller than the original activation barrier, and that is why you see the free energy shifts from here to here to here to here finally, and the number of steps that you need to go through basically depends on the extent of difference in the crystal structure between the parent and the product. In some cases it can happen directly in one step, that is what gamma gamma prime case is. Directly gamma prime comes out, you do not have any steps. In case of cementite case, you see you have one step which is the epsilon carbide. From the martensite you get first the epsilon carbide, and epsilon carbide directly gives you the cementite. So like that you can see, depending on the type of system, depending on the crystal structure complication, you can have a various number of, aluminum copper is one classic example of a large number of steps. Otherwise there are many systems where it can happen in directly one step. And now if we try to look at this from the thermodynamic angle, if you look at, you see the point is, interesting question, but the point is, once you have come to this stage, it does not bother what is the activation energy here. Now your starting state is this, the past is gone. So now you have to look at from here, if I want to come to here, what is the activation energy? Can I now reduce it by going to some other stage where the activation energy can be lower. So it is not that each of the individual activation energies, if I calculate and then add it up, will it be lower than this? It can be lower, it can be higher, but that is not the question here. So but for each step, definitely this particular activation energy will be smaller than this going directly to theta. That is what is important, isn't it? So final stage, what you are coming, is not really important. At each of the step it tries to look at what is, how do I minimize the activation energy. Now let us look at the aluminum copper. We said right now that alpha supersaturated solid solution goes to Gp zones first and then theta double prime, then theta prime, then finally theta. This is what we said. And Gp zones and alpha have the same crystal structure. This is FCC, this is FCC. The only difference is, what is the difference? Anything? Where is this lattice parameter difference coming from? The composition is different, as simple as that. The Gp zone composition is different from alpha. Alpha supersaturated solid solution has 4% copper and 96% of aluminum, whereas Gp zones are possibly the reverse. We call them as copper clusters, but unfortunately there is no easy technique to find out what is the exact composition of it, because the clusters are so small. Have you heard of what could be the technique that you can use to find out such a the composition of such a cluster? Let us say you have a cluster of about 100 to 1000 atoms. Electron mass spectrometer. Atom probe. Okay, a large number of people use 3-dimensional atom probe, where you basically can you see each atom. How many of you know about atom probe? Atom probe is a technique which is basically a field ion microscope, and where you take a sample in the form of a tip and then basically sputter away the atoms. When you are sputtering away the atoms, depending on the weight of the atom, the velocity of the atom is going to depend on. This is what we call time of flight measurements, we call them. So you put a detector at a certain fixed distance and try to see what is, once you apply a pulsed voltage and you sputter atoms, you try to measure what is the time that a particular atom has taken to reach here. Once you have done the pulsing, then you start your time t equal to 0, and then you see from time t equal to 0 when an atom is detected by the detector, and from that particular time difference you can find out, back calculate and find out this could be an element of this particular mass. If this is the mass of this element, it would take this much of time. So all this, once you know that, you can, the moment each atom reaches there, you can start assigning a particular mass number to it, and that is how you, if you do layer by layer sputtering and keep on detecting atoms and then store them, you can actually when you reconstruct the whole thing, you will be able to see how the atoms are distributed inside this in a nanometric level. One can see that, and there you can actually see if there are any small clusters of copper or of iron or whatever it is, and people regularly see this. For example, carbon atoms going and sitting near the dislocations, we call them as quadral atmospheres. This is the only technique which can actually prove that. Okay, there is no way you can see by let us say TEM, IDAX or any other technique, you will not be able to see, because the regions are so small. So this is a wonderful technique where a large number of people in the whole country, there is only one place where we have it. DMRL has this. Incidentally, I worked for 2 years on that instrument in Japan. Anyway, so that is a good technique where you can see that. So the point is, if this is a copper rich cluster and this is a aluminum rich cluster, let us look at how is the free energy diagram is going to be. Let us draw the free energy diagram. On one side you have aluminum, on the other side you have copper. You start with an alpha, let us say this is an alpha, and somewhere here is the midpoint, let us say, and so 50-50. So theta has approximately around 55%, this is what we have said. So you have a theta phase somewhere here, and let us put it slightly down, because we are, let us draw the phase diagram. We are talking of at a temperature, let us say somewhere here, maybe we can even consider room temperature, why not. At this temperature I am talking of the precipitation. I have taken the alloy to high temperature, quenched it. Why do I quench it? To get this supersaturation. If I do not quench it, then what happens? Yes, theta will precipitate at the grain boundaries. If I do not quench it, you will have, in fact this is what people observe, whenever you are doing edge hardening, unless you really quench it fast, you do not see this whole thing, otherwise during the cooling itself you can have precipitation taking place. So then supersaturated solid solution does not form. So once the supersaturated solid solution comes, and at this temperature, if you look at the phase free energy composition diagram, you will see this is the common tangent, where this composition is what? Is this composition. So this is this composition, right, and now we are talking about that this is all under equilibrium, but we are saying that equilibrium is not happening, theta is not able to come out of alpha. Then what is coming out of alpha? It is what is called the GP zones, which are nothing but copper rich, and because they are also FCC, if I want to draw the free energy composition diagram for the GP zones, how will I draw it? It will be the same curve extended towards the pure copper side. There will be no separate free energy curve for the GP zones, because they have the same structure. Whenever there are two phases with the same structure, they will have the same free energy curve. This is what somewhere we have talked about it. So you can see that this will look something like that, pure copper rich phase. So this is the GP zones free energy. If that is the case, now if I draw a common tangent between the two, then how will the common tangent look like? Okay. So this is a composition now. What do I call that composition now?
Composition of alpha in equilibrium with GP.
Correct. It is the composition of alpha in equilibrium with GP zones. What is this composition?
In equilibrium with theta.
Yes. So now let us say that this is the composition of alpha in equilibrium with theta. This is the composition of alpha in equilibrium with GP zones, and both are different. Why they are different? Because the free energies of the two phases are different, and this is similar to what we have done earlier. If you remember, when we are talking of iron carbon diagram and iron cementite diagram, we did exactly something similar, and this is a metastable phase, this is a stable phase. The composition of any phase in equilibrium with metastable phase is always higher in the solute content when compared to the composition of the same phase in equilibrium with the equilibrium phase. That is what exactly you see here. That means at this temperature, if I now want to show what is the composition of alpha in equilibrium with the GP zones, where do I show on the phase diagram? It will be to the right of this point. So that means somewhere here. I do not know exactly where it is, but that can be calculated once I have the free energy curves. Now if I say where is then the next phases, what are the next phases? Theta double prime and theta prime. and theta double prime and theta prime, they will definitely have lower free energy than what? Than Gp Jones, but higher free energy than the theta. So as a result I can say that, and they will also have the same composition as that of the theta. That is the reason why we still call them as theta double prime and theta prime, otherwise we could have given some other name. So the difference is only structure. Structure does not still become same as that of the orthorhombic. So the final structure evolves. So the structure slowly evolves from the FCC to the orthorhombic. So you will see that if I draw, I can possibly use maybe something like this. One is this is let us say theta double prime, and this is theta prime, and this is our theta. And now if I again if I look at these things and again draw common tangents, what you will see is that if I draw common tangents, now let me draw a common tangent with this and another common tangent with this. Again if I look at those points, I will see two additional points, this which is composition of alpha in equilibrium with theta double prime, and this is the composition of alpha in equilibrium with theta prime. Okay. So this is sorry, you are right. This is no right. This is correct. No problem. So Gp Jones theta double prime, theta, it will always be in that order. The composition of alpha in equilibrium with Gp Jones will have the highest solute content. The composition of alpha in equilibrium with theta will have the lowest, and it goes, because you can see Gp Jones goes to theta double prime and then theta prime and then theta. So the free energy levels, this is highest, this is lower, and this is further lower. Okay. Now if I put all these points on the free energy on the phase diagram, you will see 4 different points. One is the equilibrium composition of alpha in equilibrium with theta, and yes, we are not talking of lower than alpha or higher than alpha. For example, if that is the case, this the way I have drawn is higher than alpha. What is important is not whether that phase has higher. When I am taking an alloy of a particular composition, what precipitates is more important. In individual phases, what is important is when this is coming out of as a part of you may be saying that, sir, this should be lower than this for that to precipitate. It is not like that. You have to see for at that particular composition. For example, if I have this kind of a free energy curve, the moment I am choosing an alloy of this composition, and what will come out for this alloy when I start bring this alloy of that composition, bring it to that particular temperature, room temperature, hold it there. What comes out depends on when I draw a tangent for that particular alloy, where does the tangent intersect? That is what is going to decide. So now once I draw a tangent for that particular composition, and you will see that this tangent goes like this, and then the driving force is decided by this now, not with respect to alpha. Once I draw a tangent for the alloy composition, the alpha that I am starting with alpha. That alpha for that particular alloy I draw a tangent, and where that the tangent goes, that is going to decide this has this much driving force, whereas this has this much driving force, whereas this has this much and this has this much. Each phase will have some driving force, and depending on now this driving force, now which phase will come out, all 4 of them have driving forces, let us say, then what will come out is going to be decided by what is the activation energy for that phase. But now if I choose another alloy composition, because we have raised that question, let us look at this. If I choose this particular alloy composition and draw a common tangent, I will come to a situation like this, that this particular alloy composition is such that it can have a driving force for this phase, this phase, this phase. It cannot have a driving force for this phase. That means if I choose that particular alloy, I will not be able to get at GP Jones. You are going to see it within a minute when you look at this particular thing. For example, now if I look at these 4 compositions, this is composition of alpha in equilibrium with theta prime, this is composition of alpha in equilibrium with theta double prime, this is composition of alpha in equilibrium with GP Jones. Now if I do this exercise at different temperatures, these all being done at one temperature. If I do it at different temperatures, what will happen? At each of the temperature I will have these common tangents. At each of the temperature I will be able to generate these 4 points, and then that will lead you to different curves. You will get 4 different curves. What are these curves? They are all Salvus lines. They are different Salvus lines. We call this as a theta Salvus. We call this as a theta prime Salvus. This is as a theta double prime Salvus. This as a GP Jones Salvus. And now if you look at this particular Salvus and carefully observe what I have been just saying in answer to Anisha's, if I take this alloy, bring this alloy to this temperature, at this temperature this alloy is below the Salvus line for all the 3 of them, all 4 of them. The moment when does a precipitation take place? Whenever my alloy composition comes below a Salvus, then only precipitation happens. For example, if I take this alloy, heat it to this temperature, keep it there, will a precipitation take place? No. Why? Because at that temperature, if I extrapolate, for example, if I choose not that particular temperature, a temperature like this is easier to see. At that temperature, if I draw a horizontal, my alloy composition is having less solute content than what is the solubility limit. What is Salvus line? Salvus line tells you the solubility limit at each temperature. Am I right? So if that is the case, my alloy is containing less solute content than what the solid solution can contain, and if that is the case, then there is no chance for the precipitation. The amount of solute is smaller than what it can contain. But the moment I bring this alloy to this temperature, let us say, at that temperature again if I draw a tie line, now my alloy composition is higher than what the solute can contain, and my alloy having higher than what a solute can contain, obviously it has to precipitate. So precipitation can happen only when the solute content of the alloy is greater than the solubility limit, and that when is it happening in terms of the temperature. If I look at it, so far we talked about composition. In terms of temperature, when I bring it below the Salvus line. Now if I am at this particular temperature for this alloy composition, my alloy at that temperature is below the Salvus of all the 4 of them. That means in principle all 4 of them can precipitate. Instead, if I choose another alloy of this composition, instead of 4% copper I choose 2% copper, let us say. If I choose 2% copper, then if I carefully look at it, this particular composition at this room temperature is below the solvus of this, below the solvus of this, but it is above the solvus of this and above the solvus of this. That means the Gp Jones and theta double prime cannot nucleate from this alloy if it is brought to that temperature, and that is what I was trying to explain. If I choose an alloy of that composition, draw a tangent, I will see that the Gp Jones and theta double prime will be above the tangent. Once they are above the tangent, there is no driving force for them to precipitate. So, if I keep on shifting the composition towards the left side, you will see one by one each of the phases start dropping off, and that is why if I choose an alloy of this particular composition, the only phase that can come out is theta if I bring that alloy to room temperature, and that is why we do not use such alloy compositions for edge hardening. You will never think of edge hardening of a 1% copper alloy, because for such an alloy the only precipitate that can come out is only theta, and that theta anyway you know that it is not going to give you higher strengthening, because it is basically an incoherent. And again I should tell you, because we are talking of strengthening, strengthening is depends on, all of you know about precipitation strengthening. Whenever you have a coherent precipitates, the strain energy associated with the coherent precipitates, what is called coherency strains, can add to the strength, not only the particle and also this, and whenever a particle gets sheared by a dislocation, the new surface that is generated also has to be, a new energy has to be spent, and as a result that is why the smaller the energy of the precipitate, that means the more coherent it is, the more difficult it is for the cutting, because for cutting you are creating an extra surface. The system is already in a lowest energy state, so it does not want to create a new surface. So the stronger are those alloys which have coherent precipitates. But again there is other issues coming into picture. Coherent precipitates being very small, they can also be sheared because the size itself is very small. So the total area that you are creating when you are cutting it is not very large. So you have to look at weighing both the cases. That is why usually when you do edge hardening, the peak edging comes when you have a semi coherent interface. Gp Jones do not give you peak edging. For example, if I draw hardness versus time, you will see this kind of a curve, all of you are aware of it. This peak comes, this is the supersaturated solid solution, alpha supersaturated solid solution, and Gp Jones are somewhere here, and theta double prime is somewhere here, theta prime is here, and then finally theta is here, something like that. So somewhere between the theta double prime and theta prime is where you get the peak edging, that is where you get semi coherent interfaces. So the strengthening aspect, you do not want theta gives you now, but at the same time you will always remember that this value and this value, if you carefully observe, this value will always be higher than this, because the strengthening here is coming from what? In this case it is only solid solution strengthening, whereas here you have precipitates, and there the precipitates are larger, and the only strengthening that comes is by formation of the loops, Mod-01 loops, by the bending of the dislocations, not by the cutting of the dislocations. So that is another aspect, let us not go into the details of it. What is important for us is to understand that depending on the alloy composition and depending also on the temperature at which I am doing the edge hardening. Now I am talking of this alloy edge hardening being done at room temperature. Now if I increase the edge hardening temperature to somewhere here, let us say, why do I increase the edge hardening temperature? Diffusion is faster, so the kinetics will be faster, the precipitation will happen at a shorter time. For example, if this is one of the edge hardening curve, and if this is at room temperature, if I am doing at let us say 100 degrees centigrade, how will the edge hardening curve look like?
It will happen at short time.
short time. That means the peak is reached at a shorter time. Now can you tell me anything more?
There are no GT zones. Some zones.
I mean, I am not talking with respect to this, simply I am increasing the temperature. Okay, let us not bother about what phase is forming. The peak time decreases, and what about peak hardness? Peak hardness comes down. That is very interesting. So if you look at this, this is the kind of scenario you find. As the temperature increases in this direction, the peak time comes down and the peak hardness comes down. Why does the peak hardness come down? Can somebody tell me?
Nucleation rate is
Coalescence is one question. Something more fundamental which you can see from the phase diagram. If you look at the phase diagram, ignore all these solvus lines, just think of only one theta solvus and then tell me what would happen if I keep on increasing the temperature.
particle size will be more.
That is you have said, more than that. Solubility is more. So
there is solid solutions determining low precipitation.
Interparticle space.
the amount of precipitates will be lower, because if I look at this, I will possibly draw a separate thing. As I keep on going to higher and higher temperatures, the extent of supersaturation is decreasing. Extent of supersaturation is decreasing, and it is this which tells you what is the, if you use the lever rule, this is what which tells you what is the amount of precipitate that is forming. Go back to your lever rule, how do you calculate the amount of theta phase? The amount of theta phase is going to depend on this, and the moment I reach here it will be 0. So that is why the higher the temperature you would see, the lower the amount of phase, and that is one, and the size being higher, both of them will cause this. We will stop now.